In this video, I'm going to introduce Maclaurin and Taylor polynomials. At the end of the video, we're going to talk about the error associated with them. If you look here at this graph, what I did was I graphed the cosine curve. So that's the red curve here. So it starts here, and it goes to there, starts here, goes to there. We can write a function, so for example, cosine of x, sine of x, ln of x, e to the x, 1 over 1 minus x as a polynomial. So what I did was I expanded out 4 terms here, and I graphed it. So this is the light blue graph. So it's here, and then it separates from the cosine curve, and it goes there and there. So around here, this is called the center. So around here, the two graphs are exactly the same. I added another term to it. So that's the green curve. So it starts here, goes like this, starts to separate about here, and it starts to separate there. I added one more term, that's the purple one. So it's going to start here, goes here, starts up. So it's the same until about here, and then it starts to separate. So 2 things to make note of. So for this example, 0 is considered the center, and we'll talk about that later. But at the center, all of the graphs replicate the cosine curve. So every single graph sits on top of the cosine curve around the center. And then every curve, as I get further away from the center, it starts to separate from the cosine curve. So here's 2 examples of Taylor, Maclaurin. This is actually a series because I'm going all the way to infinity. But let's talk about e to the x. So I can expand e to the x as a polynomial, which I will teach you how to do in this video. So this is the polynomial for e to the x. If I was to choose a value for x, so let's say 3. If I plug in e cubed, and I plugged in 3, for every x value, all the way to infinity, summed it up, I would get the exact same thing. I would actually get the value of the function at that particular x value. I could plug in 4. If I plugged 4, plug in 4, 4, 4, 4, all the way to infinity, e to the 4th would be the same value as summing up the series all the way to infinity. So this works. Now there are some caveats to it. For e to the x, it works for all x values. Not the case for all functions, but we'll get to that later. But let's just assume that it works for all values of x. So I can do the same thing for cosine. Plug in some number, cosine of 2, plug in 2, all the way to infinity, exactly the same. In this video, we're just talking about polynomials. So if I was to stop this, let's say here, I can do the same thing. If I wanted to plug in e cubed, let's say 3 again, so e cubed, I can plug in 3, 3 squared, 3 cubed, 3 to the 4th, sum this up. This would now just become an approximation. So this value here is going to be off from the actual value by some amount. And just like with alternating series, that would be our error or our remainder. The polynomial plus everything else is going to be the value of the function at that x value. And we talked about at x equals 3, for example, or x equals 4. Okay, so again, the polynomial is an approximation of this. If I add the remainder in there, that would give me the actual value of the function at that x value. So why would we use this? Well, first and foremost, it's very easy to work with polynomials. If I asked you to derive this, it would be quite easy to do. But more importantly, it's very easy to integrate. And sometimes there's functions that we can't integrate. It's impossible. But if I can put it as a polynomial, then it would be very easy to integrate. We can integrate just simply term by term by term. So how are we going to generate this? You can see somewhat of a pattern to it. We have x squared over 2 factorial, 3, 3, 4, 4, 1, 1, and so forth and so on. So this all has to do with taking derivatives. because first we're going to take a derivative because we want to find, let's say, the rate of change at a point. Then we want to find the rate of change of the rate of change, which would be the second derivative, and then we do the third derivative, which is the rate of change of the rate of change of the rate of change, and so forth and so on. So the more derivatives you can add, the more accurate our polynomial will become. So here's the formula here, but I'm going to address it down here. So there's two things. We have a Maclaurin polynomial, which means that it's centered at 0. That's just the definition. So if somebody says write a Maclaurin polynomial, they're not going to tell you the center's at 0. They could say write a Taylor polynomial centered at 0. Okay, fine. They could say write a Taylor polynomial centered at 1. But if they just say Maclaurin, we assume that it's centered at 0. That's the first thing. So again, it's going to have to do with the derivatives. Now the other thing to make note of, it's hard to see in these two examples because this is part of the formula, all this in here. But the derivative is going to give us our coefficient. And the issue with this is they all came out as 1. And you'll see why here in a second. But let's kind of run through it. So here's the formula. It's going to be Fn. So this is going to be the derivative that you're taking. So if this is a 1, it's the first derivative. It's a 2, second derivative. If it's 3, third derivative. 4, fourth derivative. This n corresponds to that n corresponds to that n. And again, I want to do center at 0. So C is going to be your center. And then, so this really would just become x to the nth power. So let's just work with a center at 0. So you'd start off with, you really start off with the 0 derivative. So if I took the 0 derivative, let's say f0 of c x to the 0 over 0 factorial, we would get f of c, so f of 0, this goes to 1, this goes to 1. So you're basically finding the value of the function at the center to start. So just the normal function. That's where all of this starts. Then you're going to find the first derivative. So if I do f prime of c, so it would become f prime of 0. So since it's the first derivative, it's the first power 1 factorial. So this is giving you your coefficient. This is what's going in front of each of the terms. And then here, this is the second derivative, second power, second factorial. Again, this is what would go in the front. Now for e to the x, it's always going to be 1 because this is centered at 0. And if I did e to the x, let's say that's the function, f prime would also be e to the x. If I did f prime of 0, we're going to get e to the 0, which is 1. If I did f double prime of 0, we get e to the x, which is 1. F triple prime of 0, you get e to the 0, which again is 1. So that's why here we just have 1 in front of everything. So here's your formula on the left-hand side, which is really what I just spoke about. So they would tell you on the AP exam, or I would tell you in the test, find the 5th degree Taylor polynomial. Find the 4th degree. That's what your n will be. So if n is 4, that means you're going to go up to 4. So that means you're going up to n. So if it was 4, you just go up to 4. So you start with no derivative, first derivative, second, third, and then fourth, and then you stop. This just talks about that Maclaurin is centered at 0. So same thing here. If they wanted, let's say, the third, so if n was 3, you start with the 0 derivative, the first derivative, the second, the third, and then you stop. And that would be your polynomial approximating the function. You're approximating the function at that x value, or at some x value. This is Taylor's theorem, which we spoke about as well. So you have the polynomial, which is what we're working on in this video. On the AP exam, I always tell everybody, I hope you get a Taylor polynomial. They're very easy to do. It's easy to accumulate points. You'll see when we do this. This is very easy to do. Okay, you want to get a Taylor polynomial. The caveat to that, though, is with the polynomial, you're always going to get an error question. Because we know if I add the polynomial plus the remainder, which is everything else, we get the value of the function, which is what I spoke about earlier. So if you have this up here, this is the function. If I go all the way to infinity, that would give me the value of that. So if I stop, make it a polynomial of nth degree, so let's say 4th degree, I'm missing all of this. So all of that is your remainder. It's similar to the alternating series, but it's much more complicated here. Remember, for AST, if we did 4 terms, the 5th term was the error. So for AST, we did the first neglected term. This is the error. So just sort of take it in. You will understand it. It does look overwhelming, but this is the error for a Taylor polynomial. And I will address that at the end of the video. So I went ahead and I found all the derivatives just to save time here. So this is asking us to find the 5th degree Taylor polynomial for cosine of x centered at 0. So you always start with the function. Because it's 5th degree, I need to go up to the 5th derivative. So all I did here was just find all the derivatives. So f prime is negative sine, f double prime negative cosine, triple prime, 4th derivative, 5th derivative. So I just worked my way down. Now you have to find the value. That's going to be your coefficient. You're going to find the value at the center. So all I'm doing here is plugging in the 0. So f of 0, cosine of 0 is 1. F prime is 0, we get 0, and so forth and so on. So if you remember when we graphed the cosine, I don't know if you remember, but when I had it expanded out, there was no odd exponent. The reason is because for every odd, so f prime, so 1st degree, 3rd, and 5th, it's the sign, and the sign at 0 is 0. So that's why these all go away. So now let's write the 5th degree Taylor polynomial for cosine. So this would be one you want to memorize. So you're going to memorize. We're going to do sine, cosine, e to the x. Those are must-knows for the AP exam. So we're going to do P5 of x. So I start with this. This is my coefficient. So it's 1. Then I'm going to show a lot of work here. You won't have to do all this, but it's going to be x minus 0 to the 0 power over 0 factorial. Then we do the second one. So I'm going to write them all, even though the zeros are going to go away. We'll say plus 0, and then x minus 0 to the 1st power over 1 factorial. Now I'm here. So it'll be, I'm on the 2nd derivative, so minus 1 x minus 0 squared over 2 factorial plus 0 x minus 0 cubed over 3 factorial. And it's plus, so this is the 4th one, so plus 1 x minus 0 to the 4th over 4 factorial. And the last one is plus 0. And I'm just going to say x to the 5th. So that goes away. So all the ones in red go away. It was centered at 0, so I didn't really need to do x minus 0. So I'm going to say P5 of x. So the first one's just simply going to be, this all goes to 1, so 1. Then it's minus x squared over 2 factorial. You see how the coefficients here are just 1. And then plus x to the 4th over 4 factorial. I know you guys are going to ask me 10,000 times, do we need to reduce? It's up to you. 100% up to you. You'll see on the AP exam, sometimes it's beneficial to reduce, sometimes it's not. So it's okay to leave factorials as factorials for the AP exam. You will get full credit for that. But I did simplify it. So P5 of x, so we get 1 minus x squared over 2 plus x to the 4th over 24. For number 2, sine of x, again, I went ahead, so third degree, I went up to the third derivative, so right there. Found all the derivatives. They want us to do it now centered at pi over 6. So I plugged in pi over 6. So I did sine of pi over 6, cosine of pi over 6, pi over 6, pi over 6. So now I'm going to get coefficients now for each of my terms. So they want the third degree, so I'm going to write it here. So P3 of x equals, I start with this, 1/2. And it's going to be plus root 3 over 2. Then it's x minus the center, so x minus pi over 6 to the first power over 1 factorial. I don't need to write that. Then we come here, so it's minus 1/2. I'm at the second derivative, so it's x minus pi over 6 squared over 2 factorial. And then the last one would be minus root 3 over 2. I'm at the third derivative, so x minus pi over 6 cubed over 3 factorial. And again, totally up to you how much you want to simplify it. Once we start doing the FRQs, you're going to see sometimes it's good to just leave it and move on. Other times it is helpful to simplify because sometimes they ask you to manipulate the polynomial, and it's a little bit easier if it's simplified. But for right now, I'm just going to leave it right there. All right, for number 3, ln of x centered at 1, approximate, and then find the error. So we will address the error in this video, or in this question. So we start with the function. Again, I derived it. Remember, derivative of ln of x is 1 over x. So whenever you have to find error, you want to find the next derivative. So similar, but it's still different. In AST, alternating series, we always found the next term of the series. What you want to do for a Taylor or Maclaurin is you want to find the next derivative. So since it said 4th degree, normally we would stop here. But I did one more derivative, and I'll explain why when we get to the error. But for right now, let's just do the polynomial. So they want the 4th degree, so P4 of x. This is 0, so it's a 0 coefficient to start. So we actually start with this one. So it's 1, x minus 1, centered at 1, to the first over 1 factorial. Now we get minus 1, x minus 1 squared over 2 factorial, plus 2, x minus 1 cubed over 3 factorial, and then minus 6, x minus 1 to the 4th over 4 factorial. So that's my 4th degree polynomial, Taylor polynomial. Then it says to approximate. So they do ask you to do this on the AP exam. This is never calculator. Usually it's only out 1 to 2 terms, so it's not that big of a deal, but I would not simplify it. Okay, so let's figure out using the polynomial. So it's asking us to plug in 1.1 using the polynomial. So you wouldn't do this without a calculator, but we're going to leave it unsimplified. So we're going to get 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 3, and then minus 0.1 to the 4th over 4. So I did simplify a little bit. I simplified the factorials with the coefficient, and I just left it. But if you were to calculate this, it would be an approximation of ln of 1.1. So this approximates ln of 1.1. So there's error involved. Okay, so I think we can all agree that writing the polynomial is very easy to do. And then sometimes what they ask you to do is write the polynomial, derive it. You just derive it term by term. So it's easy to accumulate points. Again, my take on the AP exam, when you get a polynomial, it's usually pretty easy. But it's a double-edged sword, because when you get a polynomial, there's error involved. And usually they want you to find the error. And most students really struggle with the Lagrange error bound. So they want you to find the error. So I went ahead and I wrote the formula down here. So you do need to memorize this. This is a lot to take in. But understand that, just like with alternating series, if you had to do the first 4 terms, you always went to the 5th term, right? We went to the first neglected term. That was our error term. For the Taylor error, for the Lagrange, it's the next derivative. So if we wanted the 4th degree, all of this should have f5 to the 5th power to the 5th power. You're going to do the next derivative. So the way we would write this, n is still 4. So I would write r4 of x equals, I'm plugging in 4 to get f5 of z, and I'll get to that one in a second, x minus c to the 5th, and then over 5 factorial. These still all are going to match each other. X is the x value. Think of it as we did f of 1.1. So x is 1.1. The center was given as 1. So we can plug in. I'll plug in what we know. So f of 5 of z. X is 1.1. So 1.1 minus 1 to the 5th over 5 factorial. So we're going to get f5 of z 0.1 to the 5th over 5 factorial. So all we need to do is figure this guy out. So z is going to be some, I don't want to say it's an arbitrary value, but it's going to be some value that we choose. This is called the max value. Think of it like if you were to approximate something. For example, if you wanted to do, let's say, landscaping, and you wanted to purchase some rocks, and you had your square footage, it's probably safer to overestimate than underestimate. If you underestimate, you have to go back and buy more rocks. If you overestimate, you'll have some extra rocks. You can throw the extra rocks somewhere else. If you're building a bridge, it would probably be better to overestimate something than underestimate it. So your max value needs to be the worst case, the absolute maximum value that you can come up with. So it needs to be, think of it as your worst case scenario. So your z value, so z will fall, for the most part, there's a few exceptions to this, but fall between x and c. So you either going to choose 1 or we're going to choose 1.1. So your c value is going to be somewhere here and there. And normally you're just testing the endpoints. Now you will not get a calculator for this. So it's designed to work out. So this isn't the best example. This isn't an AP style question. But you're going to be given some value that you can work with, okay? So, but we need to come up with, should we use 1 or should we use 1.1? Now this is the 5th derivative. This is why you want to go out to the 5th derivative. So it's 24 over x to the 5th was f5 of x. What you need to figure out is if I plug in 1 or if I plug in 1.1, which one is going to give me the larger value. So when I divide 24 by 1, I get 24. When I divide 24 by 1.1, I don't know what it is, but I know it's going to be smaller than 24. So that means that the 1 is giving me the larger value. So this is what goes in here. So it's 24.1 to the 5 factorial. And again, I plug this into my calculator. We'll talk about calculator use in class, but for the AP exam, you don't need a calculator. They design these questions that the numbers work themselves out, that you don't need a calculator. So that's my error. So that means that when let's see if we can make sense of this. So when I use my approximation, I get some value. I don't know what this value is, but whatever this value is, it's only off by 0.002 from the actual value of ln of 1.1. All right, for number 4, determine the error, 4th degree. So we already did cosine, so I'm not going to expand out cosine again. This is just asking about the error. So what I did was I just went back to the first question. We did cosine. So I went to the 4th derivative of cosine, which was cosine. But because I want error, I'm going to do one more. So remember, you're always going to go one further than what it's asking. So I went to the next one, and I got negative sine of x. Determine the error. So let's go ahead and plug in here. I'm going to do 0.1. So my x is 0.1. McLaurin says that the center is 0. And let's see what happens here. So it's going to be R4 is equal to, so so it's R of 4, so it's the 5th of Z, x minus C. So 0.1 minus 0 would give me 0.1. And then it's going to be to the 5th power over 5 factorial. And once again, I did use my calculator, but for this, we need to come up with some value. Now for sine and cosine, if you want to pick the z value, we're saying it has to be greater than or equal to 0, less than or equal to 0.1. The problem is, without a calculator, I have no idea what the cosine of 0.1 is. The best I can say is it's positive. I know it's in the first quadrant, so I know cosine is positive in the first quadrant. But beyond that, I don't really know. And I know the cosine of 0 is 1. So there's two ways you can look at this. We can say, well, I know cosine goes from 1 to 0, there, to there, to there. So I know that cosine of 0 is going to be the largest value because it's equal to 1. So cosine of 0.1, remember, this is the first quadrant in here. This in here is the first quadrant. So it's all in here. It's only going to go down from the 1. That's the first way to look at it. The other thing you can do with sine and cosine, you can just pick 1. Because if I said to you, what's the highest value or the lowest value? Now remember, for error, it's absolute value, so we don't have to worry about the negative part of it. What's the highest value that cosine or sine can ever be? And the answer to that is 1. So we could, whenever we have sine or cosine, just take this out and just plug 1 in for it. And now I'm just going to plug that into my calculator. This is quite small. You get 0.70. So 1, 2, 3, 4, 5, 6, 7, 8, 3 with a bar over it. So I know that our error, so R n of x, is less than or equal to 0.0012345678 with a bar over it. So again, that tells me that if I go out 4 terms, so we didn't show the polynomial in this example, we did it in number 1, but if you went out 4 terms here and you plugged in 0.1 for your x, we would get a value. that value is off by 0.00000083 from the actual value of cosine of 0.1. So it's pretty accurate when you think about it. We only went out 4 terms, and we're only off by that amount. Okay, number 5, e to the x. They want us to show. So this is an AP question. So this is AP style. This almost looks like an FRQ. Maybe it is the, usually it's part D. The error is usually the last part of the FRQ. So we have e to the x, so I went ahead and I expanded e to the x. Again, we did e to the x earlier, so I'm not going to do it again. So this says, use the Lagrange error to prove that f of 0.2 minus p of 0.2 is less than 1 over 1,000. Students struggle with this. First off, just know that that's asking for error, even if you don't understand it. But I do think we could say that we take the polynomial, right? So the polynomial plus the error, or the remainder, is equal to the function, right? We spoke about that. The function at some value is equal to the polynomial, which is the approximation, plus all that missing part. If we did the function minus the polynomial, we would get the error. That's all that this is saying. The function at some x value, so f of x, minus the polynomial by plugging in that x value, so p of 0.2 is less than or equal to my error. So that's all that's all that this is asking for, is to show that the error is less than 1 over 1,000. So let's go ahead and do the error. So it's 4th degree, which means I need to go to the 5th derivative, but e to the x is so easy, right? So if I did f5 of x, it's just going to be e to the x. It's centered at 0, so f5 of 0 equals e to the 0, which is 1. So that's the first thing. So that's for the error formula. All right, so we have, so it's f5 of z, then it would be x minus the center. Now x is the 0.2, because that's what's on the inside here, right? It's f of x is your notation. So it's 0.2 to the 5th power over 5 factorial. And again, we just need to come up with this z value. A lot of times on the AP exam, they will give you that value, so you don't have to do anything. They'll often say that sometimes they'll say the max value somehow of f5 is less than or equal to 24 or whatever. They'll explicitly give it to you. Sometimes they'll give it to you indirectly in a graph, where they'll give you a graph. They'll say this is a graph of the 5th derivative. Let's say it's centered at 1, and then they'll plot it here, but this would be the value here, whatever it is. Let's say again, it's so we need to figure out what this max value here is going to be. So let's start with, we do know normally it should come between the center, which is 0, and the x value, so maybe between 0 and 0.2. The only problem here is I can definitely do e to the 0. E to the 0 is 1. I cannot do e to the 0.2 without a calculator. I have no idea what that is. But I do know it's going to be bigger. This has to be bigger than this, right? Because it's exponential. So I'm going to say e to the first is 2.718. So I'm going to use e as my max, that maximum value that we talked about. But let's just say I didn't even have a calculator for this. I might even round up and say that this is equal to 3. So we can say 3.2 to the 5th over 5 factorial. So now we can say 3 over 5 factorial is 120. 0.2 we can do as 2 over 10, which is 1 over 5 to the 5th power. So 5 to the 5th power is 3125. This can cancel with this to get 40. I can comfortably say that that is less than 1 over 1000. Okay, for number 6, it's asking us to the 3rd degree, then use the Lagrange error bound. So 3rd degree here, I should have gone out one more derivative, which I did not do that. Let me do that right now. So the 4th derivative of x is going to be 6 cosine, so 625 sine 5x plus pi over 3. Okay, all right, let's do the 3rd degree. So P3, we start with the function, so root 3 over 2 plus 5 halves. And then it's the first power, so it's just x to the first over 1 factorial. And again, this is about x equals 0, so it is centered at 0. Then the next one would be minus 25 root 3. It's the 2nd derivative, so it's x squared over 2 factorial. But then we also have the 2 from the root 3 over 2. And then minus 125 x cubed, 3 factorial with the additional 2. So I'm going to leave this unsimplified. This is my 3rd degree. All right, so let's do the error. Now, again, remember the error is going to be one more derivative than what they're asking for. So let's see what they give us. We still know the center is 0. We know that x is 1 over 15. That's given in the question here. So we're going to say R3, because it's the 3rd degree, but we're going to use the 4th derivative because remember the formula is n plus 1 of x is going to be equal to, so it's f of 4 of z, and it's x minus c, so it's 1/15 to the 4th power over 4 factorial. So you get R3 of x, F4 of z. This can go to the bottom, so 15 to the 4th times 4 factorial. This is all I need to figure out. Remember, for sine and cosine, that maximum value is always going to be 1. So when I look at the derivative here, I can assume that this part of it will all go to 1. So it's going to be 625. My max value. So we get 625 over 15 to the 4th times 24. So 15 to the 4th times 24, which is less than 1 over 1200. If you want to justify this with your calculator, you can certainly do that, but it is. And again, on the AP exam, is they will give you numbers that it's just going to work itself out. So don't be too hung up on it. This is always no calculator. Things simplify. It works out. It's easy to show that one fraction is less than the other. All right, for number 7, write a 3rd degree Taylor polynomial centered at 2. So we're looking in here. So let's go ahead and start with that. We start with first the function, so p of 3 of x. We start with 6, and then the 4 is the coefficient. It's centered at 2, so x minus 2 to the 1st power over 1 factorial, then minus 7. x minus 2 squared over 2 factorial, and then plus 8x minus 2 cubed over 3 factorial. Again, that's perfectly fine to leave. They want us to evaluate f of 2.3 using our polynomial. So P3 of 2.3. Again, this was an AP question. I don't remember. It must have been an FRQ. I would not simplify any of this. So it's 6 plus 4. We're evaluating at 2.3. So we're saying x is 2.3. So plug in the 2.3. You get 4 times 0.3 minus 7, 0.3 squared over 2, and then plus 8, 0.3 cubed over 6, if you want. So I left that there, and then they want us, so I did this on the calculator. So P, I think I did. I think I got 6.921. You could double check, but I think I plugged it into a calculator. So we're trying to figure out how far off this is. So we're going to do the error. So now we need, okay, so they're giving it to us. So I was looking in the chart here for the fourth derivative, which they did not give us, okay? But they gave it to us here. So they're saying that the maximum error is of the fourth derivative. So that's the max error, is always less than or equal to 9. That is so helpful. You don't have to do anything. So that's so it's f4 of z. Then it's x minus c. So 2.3 minus 2. So 2.3 minus 2 to the 4th power over 4 factorial. So this becomes 0.3 to the 4th over 4 factorial. All of this is just the 9. So times 9. So our max error, I put this in a calculator, is 0.0300375. So they want us to come up with a bound. So I guess that's why I did this. I feel like this maybe was an old calculator multiple choice question, which would make sense. So this is what we found it to be using the polynomial. This is my error, so now I can find an upper and a lower bound. So we could do, so f of the actual value of the function, 2.3, is going to be less than or equal to, so it's 6.921 plus the 0.0030375. The lower bound would be 6.921 minus the 0.0030375. So again, I did this on a calculator to get a final answer of, so f of 2.3 is going to be less than or equal to 6.924, greater than or equal to 6.918. All right, for number 8, they're giving us, they're talking about a third degree Taylor polynomial. So when we do the error here, it's going to be the fourth derivative, but they're giving us that. Okay, they're giving us the fourth derivative. So we have f4 of x is e sine of x. We know it's centered at x equals 0. They're saying on the interval 0 to 1. So that tells me that x is equal to 1. So x is equal to 1. So the center is 0, x equals 1. So now we're going to plug in. So we're going to get the error is going to be, it's that fn of z, which we're going to use this for. So I need to figure out which one would be, give me the larger value. So I know that the sine of 0 is 0, and the sine of 1, I just know that it's bigger than 0. So I'm looking at the sine of 1. So we have e sine of 1. Then it's x. So x is 1. is it's not explicitly given here, but if the center is 0, and we're going from 0 to 1, the x value is the 1. So we get 1 minus 0 to the 4th power over 4 factorial. You can plug this into your calculator, and this would give you about 0.0966, which would be B. All right, for number 9, we're talking about a third-degree Taylor polynomial. And again, we're talking about error. This here means we're talking about the error. So we need the 4th derivative. So they're giving us a formula that represents any derivative. So we need f4 of x is going to be 4 over 5. So all I'm doing is plugging in the 4 for the n. So they're saying about x equals 0. So f4 of 0 equals 4/5. So now we can go to our error formula. So this is the max value. This is that max value that we need to find. They're giving it to us. Okay, it's right here. So I'm going to say 4/5. And then we're going to get x minus the center. So 1 minus 0 to the 4th power over 4 factorial. So we get 4 to the 5th, or 4/5 times 1 over 4 factorial. So the answer is B for this one. Number 10, this is an alternating series. So this one is AST. So for AST, we're going to do the first neglected term. So this one's a little confusing because it's starting at 0, but that has nothing to do with this question. It's saying a third-degree Taylor polynomial. So to do a third-degree Taylor polynomial, you have to go out to n equals 3. So the first neglected term would be n equals 4. So I need to find that term. So I'm just going to plug it in. So 3 times 4 plus 1 over 2 to the 4th power would be 13 over 16. And we have x minus 2. X is 9/4. So 9/4 minus 2 to the 4th power would give me my term, that first neglected term. So it'd be 13 over 16. And then this gives me 1/4 to the 4th power. So answer here would be C. And then for number 11, 5th degree Taylor polynomial. So we're looking at the 6th derivative for the error term. So this is going to be that max value. My center. And if we're going from 0 to 1.2, that tells me that my x is 1.2, but we know that from here. Okay, so now we've got the max value, so 58.8, x minus c, so 1.2 minus 0 to the 6th power over 6 factorial, which is going to give me 0.244, which is C.